Okay, let's continue the ZAERO Advanced Training, Section 2, Aeroservoelastic Stability Analysis by the Frequency Domain Approach. So why do we need the frequency domain approach in ZAERO? The state space approach for the aeroservoelastic stability analysis formulates the ASE equation of motion in the form of first-order time domain standard state space equations. Now the advantage of this is it leads to the time domain transient response analysis for computing the dynamic loads, and these state space equations can easily be augmented by the standard control system models to provide the ASE constant coefficient equations for which the stability is computed by the standard eigenvalue extraction routines. And the state space equations of the plant model can be used to design a control system using the modern control law design schemes. However, the state space approach involves the rational function approximation, whose accuracy is sometimes questionable. Hence, it's desirable to have an ASE stability analysis capability that does not involve the RFA and which can give us the exact ASE stability result. And this result can be used as a reference solution to verify the accuracy of the RFA prior to the time domain transient analysis using the state space equations. This frequency domain approach offers a frequency domain ASE formulation that solves the ASE stability directly using the tabulated frequency domain graphs computed by the unsteady aerodynamic methods at a set of reduced frequencies, and therefore no RFA is involved. So let's review the Laplace-Domain Aeroelastic equations of motion. So first we assume the existence of QHH of S and QHC of S, which are the Laplace-Domain counterpart of the aeroelastic equations of motion, and these can be obtained by applying the Laplace transform to equation 1.1 from the previous section. And that's shown here in equation 2.1. Now, equation 2.1 can be rewritten in state space form, but with the transcendental aerodynamics being kept in the Laplace domain. So now in equation 2.2, instead of the familiar x dot equals ax plus bu, we now have s times x of s, and that equals a of s times x of s plus b of s times u of s. And note here that a and b are no longer constant matrices as they are in the traditional state space formulation, but they are functions of s. And you can see that in equations 2.3 and 2.4 where we've broken up a of s and b of s, and a of s includes the QHH of s L over v, and then b of s includes the QHC of s L over v. And our XAE of s is the state vector, which is made up of Kc of s and s times Kc of s, where s times Kc is analogous to Kc dot in the state space formulation. And then finally, our UAE is delta, s times delta, and s squared times delta, which is analogous to delta, delta dot, and delta double dot. Okay, so next let's build up the Laplace domain plant model. The state space equation for the sensor can be expressed in the following general form of equation 2.5. And for the displacement sensor and velocity sensor, the sensor matrices are the same as the state space equations shown in equations 1.24 and 1.25. And for the acceleration sensor, the sensor output can be derived from the second block of rows in equations 2.3 and 2.4 in the same way that we did in the previous section, shown in equation 2.6. Now, combining equations 2.2 and 2.5 with the state space equations of the actuator model expressed in equation 1.31 yields the plant state space equations, but with the transcendental aerodynamics being kept in the Laplace domain. So now in equation 2.7, we have our plant model, S times XP equals AP times XP plus BP times UP. And our AP, the A of the plant model, is made up of AAE, BAE, and A actuator. And then BP is just made up of the ZAERO matrix and BAE. Our state vector for the plant is now augmented by the actuator states, X actuator. And then our input for the plant is just the input to the actuators. Next, let's build up the closed loop state space equations with the transcendental aerodynamics. So the state space equations of the control system model, but in the Laplace domain, are now expressed in equations 2.10, where we have the subscript C denoting the control system model. Now the open loop ASC equations of motion for the uncoupled ASC and control system can be expressed in equation 2.11, where we use the subscript V. So now AV is made up of AP and AC. And note here that AP, the A matrix from the plant, is a function of S, whereas our control system model, AC, A is a constant matrix. So our ABCD matrices are directly the same as they are for the state space equation from the previous section, but now we're just augmenting the closed loop model with these control matrices. And then our states in equation 2.13, XV is now a combination of XP, the plant states, and XC, the controller states, and then the same thing for our output and input. Now equation 2.14, the ASC loop is closed by applying the gain matrix GV. So the resulting closed loop equation is 2.15. So we have S times XV of S, which equals A bar V of S times XV of S, where A bar V of S is given in equation 2.16. Next, we're going to apply the G method to solve this closed loop equation. So the closed loop matrix A bar V of S contains the Laplace domain gaffs QHH of SL over V and QHC of SL over V that are not available because only the frequency domain gaffs can be generated by the frequency domain unsteady aerodynamic methods. However, based on the G method, because A bar V of S is analytic in the entire Laplace domain, it can be approximated here in equation 2.17. So A bar V of S can be approximated as A bar V of IK plus G times the partial derivative of A bar V of IK with respect to IK, where SL over V is equal to G plus IK. Now A bar V of IK is obtained by replacing QHH of SL over V and QHC SL over V by QHH of IK and QHC of IK, respectively, in equations 2.3, 2.4, and 2.5. So that gives us equation 2.19, where we now have XV in terms of A bar V of IK. Now the resulting eigenvalue problem for G is given in equation 2.20. So we have dV minus G times the identity matrix pre-multiplied by XV equals 0, and then dV is given in equation 2.21. So now we can extract the frequency and damping of all of the roots. So at a given pair of velocity and air density, the flutter solution can be obtained by applying a reduced frequency sweep technique to search for the roots, and a predictor-corrector scheme to ensure the robustness of the sweep technique. Now, because the size of the closed loop state vector expressed in equation 2.13 is 2 times the number of modes plus 3 times the number of actuators plus the number of control states, all of the roots can be extracted from equation 2.20. And the G method procedure is designed to extract modal frequency and damping values at a given set of air density and velocity pairs at a certain Mach number, which yields the VG and VF diagrams. And of course, flutter of the closed loop system occurs at G equals 0. So now let's compare the frequency domain approach and the state space approach for the ASC analysis. Now, in addition to the ASC stability analysis, the state space approach provides a foundation for the time domain dynamic loads analysis, such as maneuver loads analysis, discrete gust analysis, store ejection loads analysis, and the nonlinear flutter analysis. However, the accuracy of these dynamic loads analyses relies on the accuracy of the rational function approximation, and that depends on many input parameters, such as the number of aerodynamic lag states, those aerodynamic lag state values, and the types of constraints imposed on the least square fit procedure. So the question is how to determine the best input parameters for obtaining the most accurate results, and this requires a reference solution of the ASC stability analysis. And a reference solution can be generated by the frequency domain approach because it does not involve the RFA, and therefore it's considered an exact method. So we always recommend that prior to the dynamic loads analysis, the ASC stability analysis first be performed using the frequency domain approach. And this will give you a reference solution to compare the RFA results to. And the best input parameters involved in the RFA can then be determined by comparing the state space solution to the frequency domain solution.